Welcome back, Chemistry 30. This is the 16.2 booklet, Heat and Chemical Reactions and Processes. And it corresponds to 496 to 500 in the textbook. And in this booklet, we'll be looking at calorimetry, thermochemistry, systems, surroundings, universe, enthalpy, and enthalpy of reaction. Differentiating between endothermic and exothermic reactions, and describing how a calorimeter is used to measure energy absorbed or released. And finally, explain the meaning of enthalpy and enthalpy change in chemical reactions and processes. So we've mentioned this before. Endothermic reactions, heat transferred from somewhere else, the surroundings, to the system where the reaction is taking place. So heat is absorbed. Endothermic begins with En, so think of it as entering. Heat is entering the area in which the reaction is occurring. Exothermic, heat is transferred from the system where the chemical reaction is happening to the surroundings. So it's being released. It begins with Ex, so think of it as exiting. Heat is exiting the area in which we're studying. Calorimeter, it's an insulated device used for measuring heat transfer. It could be something as simple as a styrofoam cup, which helps contain heat within it, or it could be one that costs thousands of dollars, that, like a very expensive thermos that ensures that any heat remains inside. So used for determining the amount of heat involved in a physical or chemical change. It operates by looking at heat transfer occurring between reaction and the water that's inside the calorimeter. Any temperature change of the water can help determine how much heat was lost or gained by the reaction itself. And one common experiment that we could do here is looking at using a calorimeter to determine the specific heat of an unknown material, how that material absorbs or releases heat. So the little experiment you would do would involve heating up a piece of, if it's unknown metal, to a certain temperature that we would know, having our calorimeter, which contains water, at a certain temperature that we would know. Then, of course, once that hot metal is put in there, it transfers heat to the water until the metal and the water reach a final temperature. And the idea is that heat lost by the metal is equal to heat gained by the water. And of course, let's say the heat gained by the water is 10 joules, the heat lost by the metal is 10 joules. Of course, that would be a negative 10 joules. And of course, negative 10 does not equal positive 10. So we'd have to put a negative in front of the heat lost by metal to change the negative to a positive. So to make it mathematically correct, we have to have a negative on one side. And of course, since Q is equal to Cm delta T, negative Q equals Q, so I can say negative CMT equals CMT, with the left-hand side here pertaining to the metal, and the Q on the right-hand side pertaining to the water. So the CMT is the specific heat of the metal, mass of the metal, temperature change of the metal, equals the specific heat of water, the mass of water, the temperature change of water. Okay? And we'd be able to figure out all of those things. The only unknown would be the specific heat capacity of the metal. So initial temperature of metal, measured. Initial temperature of water in the calorimeter, measured. They both reach the same final temperature, so that'll be equivalent. To figure out the change in temperature, it's Tf minus Ti, Tf minus Ti, and of course we'll get a negative temperature change here for the metal because it's losing heat, and a positive temperature change for the water because it's gaining heat, so the negatives will cancel out. Mass of the metal, mass of the water, and specific heat of the metal, and if I'm using liquid water, the specific heat of water is 4.184 joules per gram degree C. Okay, so that's how we would do it, using the idea that heat lost equals heat gained. And of course, we're assuming that there's no heat loss out of the container itself. We're assuming 100% of the heat from the metal is transferred to the water. So if you had an expensive calorimeter, that in fact would happen. But if we're using a coffee cup here or some other thermos, there would be heat loss, so there would be some error being involved. Of course, we need to know how much water we have. The volume is converted into mass, so that, of course, is required here. So that's the answer to 4A. So here's an example using that. A sample of silver. So we're told it's silver, so we're therefore being asked to find something else except the specific heat. It has a mass of 63.3 Gs. It's heated to a temperature of 111.4 degrees. Okay, so that's where we're at there. The final temperature of the silver and water is 19.4, and the water was initially at 17. Assuming no heat loss, what mass of water was in the container? So again, we're looking at, oh, and we're also told that it's water, of course, so 4.184 is the specific heat of water, and silver, 0.24 joules per gram degree C. So all of this information we can get out of that paragraph there. The mass of silver, the initial temperature of silver, the mass of water we're asked to find out, so that's the question mark. The initial temperature of water is 17 degrees. They both reach the same final temperature of 19.4. Specific heat of silver, specific heat of liquid water. The temperature change, 19.4 minus 111.4, we get negative 92, which is fine because we are losing heat with the silver, so that makes sense. And 19.4 minus 17, 2.4 is the temperature change for water. So using the idea that Q metal equals Q water, when I take the negative, heat lost equals heat gained, CMT equals CMT for metal compared to water. You can see this is our unknown here, and we've determined everything else here. So the specific heat of metal, 0.24, mass, 63.3, temperature change, negative 92. Liquid water, 4.184, mass is my unknown, and temperature change, 2.4. So I need to isolate M. And of course, on the right-hand side here, I have 4.184 multiplied by M multiplied by 2.4. So to undo multiply, divide by 4.184 and 2.4. Of course, what you do on the right-hand side, you have to do on the left-hand side. Those numbers cancel out. And my equation becomes mass is equal to everything here you see on the left-hand side. The negatives will cancel out. I'll be left with grams. Works out to be 139.9. Sorry, just 139 grams. That's it. So the tricky thing is just pulling out all that information from the question and using it in the formula there. Question C here, explain how you design an experiment to determine the specific heat of a 45-gram piece of unknown metal. So we'd already discussed this. Of course, we'd heat up the metal to some initial temperature, place it in a calorimeter with a known mass of water and its initial temperature, note the final temperature, realize that heat lost equals heat gained by the water, or as an equation, negative Q metal equals Q water, or negative CMT equals CMT. Here's the metal side, here's the water side, so just rearrange and solve. So quite easily done there. The previous question was similar to that, except we weren't looking for a specific heat capacity, we were looking for mass of water. Thermochemistry, the study of heat transfer and chemical changes, and also phase changes. Okay, I think we'll stop there. This will be the end of part 1. We'll continue on with part 2 in the next video. So hopefully we see you shortly.